Okay, thank you, Cloud Person. Recording in progress. Good morning. Uh, Brain hiccup. Today, we're going to spend the time as quickly as I can. I'm going to skip over student examples of something I call the 4 points in the interest of time. But what I want to do is finish a little early today for this morning session to give you extra time to work on your circuits for the 4 LED bounce chaser. And then we're going to use the afternoon session in its entirety to build the circuits. Okay, but before we begin, the administrative stuff, oops. In honor of tomorrow's storm, we might get 2 feet of snow. Boom, boom. All right, there we go. And so I won't belabor the reading. Please make sure you're keeping up with the reading. I won't test you on it per se, but it is important to your understanding the material, particularly as most of the projects will be based on that material. Okay. Project number 2 is out. It's due this coming Tuesday at 11:59 seconds. Now, some administrative stuff. There's a solution that we're crafting, we being the department, to get you access to this room, to leave the kits here in a cabinet once it gets purchased, so that you can enter the room outside of class to work on your projects from your kits as a group. And so one of the solutions proposed was to elect what I call key masters. And those people will have their Clark ID activated to be able to swipe to open up the room. But with privilege comes responsibility, right? Usual life thing. If you are a key master for your group, that means anytime your group wants to access the room to enter it, that's something you're going to have to negotiate. Now, certainly that would be outside of class meeting times, right? There are times, as I understand, where TAs for classes that have TAs will be here and the room will be kept open most nights of the week. And so that is being made available. But the scalable solution is to have members of each group, and I'm thinking 2 members per group, be designated as what I'm calling key masters. So we have 4 groups. One group I'm calling group 1 for lack of a better name. Nguyen, Tyler, Adriana, and Jamie. Why don't you pick 2 of you to be key masters? And you can tell me afterwards, okay? And then the second group, Caleb, Jack, Cushman, and please tell me if I'm pronouncing it wrong. Kian, sorry? Kian, thank you. Kian. And Kian, please pick 2 to be key masters. And group 3, Han, Jinwei, Locke, and Nathan and Keegan, please pick 2. And then Sujan, David, Dilasha, please tell me if I'm mispronouncing your name. Don't be shy about it. And Min, please pick 2. So by the end of today, pick 2, let me know, or at least the end of the morning, and I will write them down for them to Dr. Basie, who will then code you into the access, okay? All right, any questions? No? As was written in the assignment that was due on Tuesday, and thank you for your submissions, I'm looking through them now, you will all be giving a 5-minute presentation, each group, and so let's designate one person for each group to connect to oh, you know what? I didn't give you the link. I knew there was something missing. Oh, wow. All right. There's a logistic that I missed. All right. In the Moodle site, there is a, brain hiccup. There's a link to my Zoom room, and we can have one person from each group connect to my Zoom room and give the 5-minute presentation. Let's do that towards the end, since that's a logistic I didn't prepare for. I forgot about that. Okay. Any questions? No questions? Everyone's week is good? Everyone looking forward to the snow? Yeah? No? All right. So why don't we continue on? And so where we last left off, we talked about this thing, electricity, and we began it with a discussion of the structure of atoms, because it's the electrons that flow, which is this thing we call electricity. And we talked about the so-called free electrons, and these free electrons are a consequence of atoms wanting to be stable. And they achieve that stability by trying to, as much as they can, fill their valencies. And they do that in a number of ways. We talked about sharing, but we also talked about either donating or accepting a free electron. And so some materials, primarily metals, are such that these free electrons flow very easily, so-called conductors. And we talked a little bit about gold being a good conductor. And the converse of conductor is something called an insulator, something that does not allow easily the flow of free electrons. And we said these electrons will bounce around, being donated and accepted, donated and accepted among valencies for nearby atoms. And this flow of free electrons is called current, measured as amperes or amps. Okay. Any questions about this? No? To jar your memories. All right. So we also ended with a brief discussion of various so-called components, and you put some current through these, or apply voltage if you want to think of it that way. And these components shape or change the electrical signal. And the whole goal with electronics or electrical engineering, what have you, is to try to shape this current and voltage in a way that you can get it to do productive work in all sorts of desirable ways. Okay, so let's talk about finite state machines. And a finite state machine is used all over the place in robotics and more generally in any sort of computation that's structured as this sense, think, act type of cycle. And so I'm going to go over a technique that talks about how you structure your finite state machine computation in a methodical fashion. And I know that people want to just jump right to implementation, but I will implore you, please resist the temptation to want to jump into the solution right away. Follow the methodological process, because in the examples I give you, they'll be simple because I want to use this opportunity to teach you the approach. But as the example gets more and more complex, you have more sensors, more interactions, more actuators, and so forth, it's going to get complex, and you won't be able to just jump right to the solution. So while the idea is relatively simple, please use the opportunity to practice the design approach, okay? And I promise you it won't let you down. All right, so in this example, suppose we have a fictitious example with a robot, because I see everything as a robot, and you want this robot to implement this so-called bump and turn behavior. And so this bump doesn't necessarily mean it comes into physical contact, and next week we'll look at a range sensor. The idea is that when you get close enough to some obstacle or object in the environment, you sense it, this idea of a bump, danger, danger, too close, you turn around and you proceed going forward in the other direction. And so in this explanation, this sort of high-level algorithm, we have a parameterized description of it. And so when I say parameterized, you'll notice here, when I say things like distance, I say D. Distance D could be 1 centimeter, could be 10 meters. It doesn't matter, right? It's just a variable. So we start out in step 1, and the robot moves forward some small distance, okay? It then goes to step 2. It checks to see if it's too close, if it has bumped, touchless bump in this example, into some object in the environment. If there's no bump, it goes to step 1 in proceeding to move forward. Otherwise, it turns around some prescribed angle A, okay? A is just a parameter, doesn't matter what it is. And then the next step after turning, it goes back to step 1. Now, this is fairly simple. Now, these behaviors can get very, very complex. And if you're here in the fall, you'll find out how complex it can get. We'll have a robotics course come this fall. I'll be teaching that. Shameless plug. All right. So a finite state machine is a graph, and you see graphs all over computer science. They're a very immensely useful data structure because there are a whole host of algorithms for doing all sorts of wonderful things with a graph. And if you can take a problem and reduce it or transform it to a graph, you have available to you all of the amazing tools for operating on graphs. And so in our use of graph, it's a directed graph. So you notice all of the arrows or edges connecting the states or circles have an arrowhead. And that arrowhead implies, well, this is the direction in which you will move. And in this case, we have a state in this picture, and you're transitioning or changing from one state to another. So what exactly is a state? A state is some computation. It's the execution within an algorithm of some step. You're doing something. An arrow describes the ordering. We have step one, then do this next thing, then do that next thing under these conditions. And so the arrow is an ordering among these algorithmic steps. Now, for the sense, think, act aspect of it, you'll notice this edge or arrow or transition, and I'll try to use synonyms wherever possible, it's decorated, it has an annotation. Now, in robotics or sensor-based applications, this describes an observation, a sensor value, okay? And so if you have a certain sensor value, you're gonna trigger the transition from state one ending up into state two, which are both behaviors. Okay, any questions about this? No? All right. Now I take it you've done finite state machines and algorithms? Yeah? No? Not necessarily? All right, so I'll continue on. So if you're gonna code this bump and turn behavior as a so-called finite state machine, well, there's a prescriptive series of steps that you follow to make it easier, but also less error prone or fewer bugs. You start out with a problem. After defining your algorithm, that's always the first step. And it doesn't have to be full code, could be just sentences that are numbered. You define your states that you need. You create a switch over states, just like switches in Java. You wire in your transitions, and I'll talk about what I mean by that. You'll add your conditionals, and then you'll add your functions, and those functions are the API calls that you'll use for whatever system, sensor, actuator you're using to implement the behaviors that you're describing as your states, okay? All right, so here, this always happens after, let's see. Nope. Let me, there we go. So I'm repeating the algorithm for bump and turn, and we have a number of states. You start out moving forward, that's a behavior. So we have a state called forward. We have a state called check bump, we're doing something, and we have a state called turn around. So the transitions, okay, you start out and you have what I learned is called the lambda move. You transition through no sensing action from moving forward to checking bump, okay? So after the move forward behavior has halted, you transition without reading a sensor to check bump. Then check bump has a transition going back to forward. And that's from the condition where your sensor for bumping triggers and says, aha, I'm too close, or I've virtually touched something. That will trigger transition back to forward, and you notice the decoration on that edge is no bump if there's no bump. And there's another decoration if you have bump that transitions from check bump to turnaround. Now, one of the observations here is if you look at the state check bump, you will see that there are two outbound edges emanating from it. That means programmatically you're going to have a conditional. And we'll talk about how you wire in the conditions in this methodical approach for implementing finite state machines. Okay, and then lastly, turnaround has a lambda move to forward. You don't need a sensor condition to trigger that transition. Okay, any questions about this? That make sense? No? All right. So you start out, and because we're implementing on the Arduino platform for this segment of the course, and you have a number of necessary parts in the anatomy, so to speak, of an Arduino program. You start out at the top, and you might have a number sign include, that's a preprocessor command, and inside the angle brackets is the name of a header file, .h, and that's nothing more than a text file, and in that header file are the definitions of functions from libraries that you'll be needing for various libraries. So one of the includes that we saw before was number sign include Wi-Fi Nina.h. Now, going hand in hand with this number sign include is going to be adding the bytecode for the library definitions. And so we did a number sign include Wi-Fi Nina.h, and then we went through the menus and did sketch add library, add zip library. So if you're going to use a library, you need to do two things. Have your number sign include so that your program knows the definitions for all the functions from that library. And you need the bytecode for that library because those are the implementations in binary that the processor understands. Okay, any questions? No? So then you have a section where you might have your descriptive things, your so-called preprocessor macros, number sign define, some string, space, another string. And this is just for beautification of your program. Because when your programs get more complex, maybe there are values like the number of iterations or the LED that you're going to identify by its pin for digital I/O, right? And so this number sign define, when you run the preprocessor as a part of compiling your program, is going to take every occurrence of this first string and replace it with the string afterwards. So you can have values, you can have strings, all sorts of things. Is just a replacement. Okay. Any questions? No? All right. And so then in the next section, you would put global variables. Now, global variable is just a variable, and in C++, of course, you have to give the type as well as the name. And it's a really, really important idea to initialize it. Unlike Java, there's no object initialization. In C++, it's whatever that piece of memory happened to contain when it allocated that variable in memory, it's going to assume that value. So you always want to be in the habit of assigning an initial value to all of your variables. Now you could do it at the declaration for the global variable, int iterations equals 0, semicolon, you need that semicolon. Or if you don't do it in the declaration, you could initialize it in the setup routine. But you have to guarantee the state of all of the variables in your program. Now, these global variables will persist in their value between runnings of this loop routine. And as we said before, this setup routine is called every time you power cycle the board. That includes plugging it in as well as hitting the reset button. And this loop is called again and again and again and again and again. Okay. Any questions? That make sense? And so this is our general anatomy of an Arduino program. So let's go back incrementally to coding our finite state machine. So we've done our algorithmic description. We've drawn the finite state machine. So programmatically, the first thing you do is you define your states. And I'm choosing to use number sign defines as the names of my states because I'm going to use a switch statement to define the behavior of my state machine. Okay. So then the next thing we do is we need a state variable. And that state variable is going to be used for the system to select which particular behavior is going to be executed for a particular run of the loop routine or at a particular time. Okay. And so the next thing we have is also a state driver. So I'll have an empty while true. So what are we going to do? We're going to run again and again and again and again this logic for the FSM. Any questions about this? No? All right. So then we create what I like to call a switch sandwich, right? Why do I call it a switch sandwich? Because, I'll say that in the next slide. But a switch statement, to jar your memory, I don't know if you did it in Java or not, a switch statement is the equivalent of having a sequence of if, else if, else if, else if, else conditionals. It's a lot more compact, it's a little bit more elegant, and it's a little easier to understand. So the semantics of switch says, we start out and we have this parenthesized expression in the switch statement, that keyword, and this value has to evaluate to an integer, right? And when it evaluates to an integer, based on the value, your execution is going to select one of these blocks of execution called your cases. So this would almost like be saying, if state is equal to 1, then do this. Else if state is equal to 2, do that. Else if state is equal to 3, do that. Else, do that. And so each of these cases is like saying if this variable is equal to a certain value, and the corresponding break ends the block for that case. Down below, you'll see there's something called default. Default is not required, but it's good programmatic practice to have default just in case your variable might take on a value you don't expect, like you forget to initialize it. Any questions about this? Does that make sense? All right. So we have a while loop, and sandwiched inside of that is a switch statement, hence the name switch sandwich. Now, we just got done saying a little bit ago that this loop is called again and again and again. So for the Arduino, you would imagine instead of a switch sandwich, it's a loop sandwich. It's the loop routine which envelops this switch because that loop routine is taking the place of that while true. This loop is called again and again and again and again, okay? So there's the difference for the Arduino. If you were writing a self-contained finite state machine, you'd use a while loop enveloping your switch. But on the Arduino, you're going to put that inside of your loop routine. Okay. Any questions? No questions? All right. So let's continue on. And we have each one of our behavior blocks. The cases are going to correspond to the behaviors implemented by each state. And you'll see here, everywhere I see forward, that's equivalent to the number 1. Where I see check bump, that's number 2. And turn around, it's number 3. It's a lot easier to understand what's going on in the program. I could easily or equally have said case 1 colon, case 2 colon, case 3 colon. But if you give someone else this code, like your group member, maybe you're collaborating on developing different state behaviors, they're not going to understand as easily what's going on. And so this number sign define, this preprocessor macro as it's called, is just useful for us as humans. Make it more readable, self-documenting code. Okay? Any questions? No questions? All right. So let's go ahead now and let's wire in the transitions that we had in the original finite state machine graph. So we had a forward transition from the forward state to check bump. And how you implement the transitions is the last thing you do in each case is set your state variable to whatever the next state is going to be. So here we go from forward transition to check bump. So at the end of that case statement for the switch case that implements the forward behavior, we're going to set state to check bump. All right. So next thing we do, we had if there's no bump, okay, check bump transitions to forward. So we go to the state behavior implementation for check bump, that case, and we set the state variable, last thing we do, to be forward. That's the next state, going out of check bump. And lastly, turnaround had the transition from turnaround to forward. So we go to the case statement implementing the behavior for turnaround, and the last thing we do is set state to forward. That's going to be our next state. And so each time it's run, it'll implement these transitions, but we're not done yet. Because recall, we had a conditional here because we had 2 outbound edges from check bump. All right. At this juncture, it would be very useful to test out the transitions that you've wired in thus far for your finite state machine. And so you could use the print statement, serial.println, which is an Arduinoism, to print out state is forward. And so it's useful to track the behavior to kind of do a double check to make sure that the logic that you're trying to implement is actually happening when you run it, okay? And so here we have a serial print line, and before moving on, you test it out. Now, one of the things that you'll notice is, of course, I haven't implemented all of the transitions. When you start out wiring your transitions, focus on the positive logic. If the following thing happens, this is my transition, not the negative logic, because it's easier to think of the positive logic. Okay. Any questions? No? All right. So now we add in our conditionals. And a conditional in your finite state machine is a node whose out degree is more than 1. because in order to select one of these transitions, you have to evaluate a condition that determines which one of these alternatives are going to be taken. So here we have for check bump, if there's no bump, you transition to forward. If there is a bump, conceivably from your sensor, you're going to transition to turn around. So now we introduce another variable. Here we have a Boolean, is bumped, and it's going to be initialized to false. All right. So now we take our check bump and we set our state condition on whether or not is bumped is true. That's how you implement a conditional, a branching point, or an out degree that's more than one for a particular state. And now that you've done this, you could test your transitions. You could put your serial print lines in, and then you set is bumped to false. It'll take this transition, and you'll see those prints. Then you go and set is bumped equals to true. It'll take this transition, and you'll see those states printed out. Again, incrementally test your logic. Any questions? Does that make sense? Yeah? All right. So now, okay, that's where you go to the API calls. Now, suppose we had an API call called drive command, and we had an API call called get bump sensor, and we had an API call called turn command. That's where you go to the manual for the APIs for your system, and you implement the behaviors for each state about what it means to drive forward, what it means to turn, what it means to check the bump sensor. At this juncture, we know the transitions are correct. Now it's implementing the semantics of these behaviors. So drive command, 1010, this is just made up. It'll get it to drive forward some amount. You have get bump sensor, sets the value of your conditional, which you've already tested. And then turnaround, maybe it's turn command with some angle. And now you know it's going to work. It's just tuning. Okay? Are there any questions about this? All right, so please resist the temptation to want to jump to this, right? Be methodical about it, and you'll get fewer bugs, have fewer headaches, but make sure you go through the design and the incremental testing. Okay? All right, any questions? All right. So design your behavior, parameterize it where possible, write down your algorithm, draw your FSM, your graph, and then you code it. Start with the constants for the states, initialize your state variables, make a switch sandwich, wire your transitions, focusing on positive logic, add your conditionals, and then look at your APIs to fill in the semantics for each state. Okay. All right, no questions? No? All right. So this next part is an approach that I've used several years, and I didn't invent it. It's derived from something that I learned in industry. And it's for structuring open-ended projects where you start with a high-level description and you walk through, at the end of the process, a functioning prototype. And so all of this is prescriptive, but it's important, again, to follow the process. And so this is based on something called the Heilmier Catchecism, and it's named for George Heilmier, who was a director for DARPA, the Defense Army Research Projects Agency. And it became a standard that was used in various scientific engineering circles for how you structure questions to evaluate large engineering type projects, right? And so I learned this, and I've developed over time a version that works really, really well with undergraduate and graduate level scientific and engineering projects. And so it's called the 4 points, don't have a better name for it, and it consists of 4 basic points. What's the context? What is current state of the art? What will you do? And what is the impact? So let's talk briefly about each of these, and you'll have an opportunity to practice this with project number 2 that's coming up on Tuesday night, due Tuesday night. And so what's the context? With the context, you're effectively answering the question, who cares about what you're trying to do? Just because you can do something, it doesn't mean you should do something. You need to justify why people should be interested in what you're enterprising to do. And so what sort of things do you talk about to answer this question? Is it worth the time, energy, and resources to pursue what you're trying to do? Well, in doing so, you need to explain the size and scope of the problem. Who's it going to impact? And if it's going to impact someone, what are the attributes for that particular cohort of people that you're trying to propose this solution for? Now, of course, if it's only one or two people, might not be that interesting. And so in business, people call this market segmentation. You have to identify the market for whom your solution is going to be applicable. Is it going to solve some problem in their life? Well, who is the they? Okay. Now, of course, you have to come with data. You can't just make bold assertions. You should put yourself in the posture of saying, don't believe me, believe these trusted sources. According to the United Nations report on population, by the year 2050, the population will grow to blah. That's going to put pressure on food systems, right? You need to cite your sources, right? That gives you a much stronger justification. And use hard facts when you justify what it is you're trying to do. So moving on to the next point, what is state of the art? And this answers the question, well, how are people currently addressing this? And that's really, really important. It lets your audience know that you understand the problem deeply, okay? But don't be arrogant or naive to think that you're the only person in the world who's ever thought of it. It's okay to search the literature. In fact, you should search the literature and find how others have solved this problem or how others have solved a related problem. There are many articles, both academic published and non, that talk about all sorts of things that people have done. Look them up. And the reason for that is that not only will you learn some of the underlying principles about the problem, you'll also learn from their successes and their mistakes. How have others tackled it? And if you read enough of these supporting sources, you'll start to be able to place them in categories of solution approaches, right? 10, 12, 20 of them, as many as you can find. There are only so many different ways people have thought of things, even though people have thought of a lot of things. And once you place them in categories of solution approaches, you'll be able to identify what these types of results are. How have they solved it, and what did they find from this way of solving it versus that way of solving it? And what it does is it builds that deep knowledge of the background, but it also starts to highlight any gaps in implementations or solution approaches. And you'll begin to use this to motivate how can you improve it. Take, for example, timepieces, watches. Now, in the olden days, I should say, they were mechanic. And one day somebody had the thought, gosh, well, these watches are great, but you can't get them wet, right? Now, it might seem silly by today's standards, but watches weren't always waterproof. Now, why would you want a waterproof watch? Maybe you're in an environment where there's a lot of water, or you're scuba diving, right? There's a fairly large community of scuba divers. And if you only have 30 minutes of air in your tank, and you know it's going to take you 5 minutes to dive and 5 minutes to come up, you want to make sure you don't spend more than 20 minutes underwater, right? And so this is a really important issue, or rather point. How can it be improved? Well, how do you know how to improve it if you have no idea how people have been trying to solve it? Okay, all right. Now, your project and prototype that you build is intended to address this gap in state of the art that you identify. It could be maybe there's no mobile solution, or maybe the existing solutions are very expensive, or maybe they use fancy sensors that the average person is not going to buy. But you still need to go out, and there's no substitute for looking at current state of the art. Okay, any questions about this? No, make sense? All right, so then the next thing, what will you do? Now this answers the question of how will you carry out addressing this gap that you've identified. Now, this is where your architecture comes in. The functional components that together build the prototype that addresses the gap for the people you've identified. Okay, so you define your architecture and keep it simple. Boxes and arrows are fine. And if you were doing this in industry, you'd have a graphics art department, right? You don't need to light the world on fire with beautiful artwork. If you choose to, that's great, but simple boxes and arrows does the trick. Now, the boxes represent the high-level components in your system. They do something, and the arrows represent the data flow. Outbound arrows are data that's sent out from a component. Inbound arrows are data that is accepted by your component, regardless of if it's local or across the network. Now, once you have your data flows and your boxes, give everything a descriptive name so that someone can see, all right, not a Mac Store 7005, storage, right? What does it do? Give it a nice descriptive name, as well as a high-level description about what that behavior does in the context of your system. Now, do this completely for everything in your system. Don't leave any arrow and any box in your architecture untouched. Now, absolutely, in software engineering, you learn about different documentation standards. That's not what this class is about. Absolutely, you can use those standards, but this isn't a software engineering course. But nonetheless, be complete. Someone should look at your diagram and understand what the role is of each component, what the data inputs are, and what the data outputs are, the inflows and the outflows. Now, collectively, all of the interactions between the components in your architecture are going to be built into your prototype to provide this solution that addresses the gap that you've identified. Okay. Any questions about this? No? All right. So now, once your architecture is complete, you have these descriptions, you have the boxes and arrows, that's when you assemble your tool chain. You have to decide for each box and each arrow, what language are you going to use? Python, Java, Scala, something else, and why? What framework are you going to use? Are you going to use Hadoop? Are you going to use, what are you going to use? And why? The why is equally as important as the what. What tools, APIs, components, and everything you're going to use to implement your behaviors and the data flows. Is your data going to be text? Is it going to be JSON? What are you going to use? And why? Now that you assembled your tool chain, you're going to begin the process of implementing the descriptions, high-level behaviors. Because if you just said stores, there are many ways to store, but time is finite, and you have to decide what's important to you. In business, they'd say you want to focus on your core competencies. And what I mean by that is this classic engineering trade-off: buy, build, or customize. So buy means you have a complete solution. It could be something for pay, could be something for free, wonderful, but this complete solution solves everything you're trying to do. Build means that you create it from scratch. Now, buy can be expensive, and you're beholden to whatever the agreement is with the company that sold it to you or you acquired it from. Build can be very time consuming. Now, if you were going to, for example, for your project, draw diagrams, you wouldn't say, as part of my project, I'm going to create a drawing program. That's a waste of your time, because that's not what your focus is. If the focus of your project is analytics, don't spend all your time on NoSQL storage mechanisms. You have finite time, and you have to decide where you're going to spend that time. Now, customize is in between buy and build. Customize says you find something that solves some or most of your problem for the behavior of a component, and all it needs is a little extra customization. Maybe there's an engine that performs a type of calculation that you need, but it's a library that you call through a program, and you need to wrap it in a server so it's network accessible, right? And so this idea of customize is often where people recover time on projects for things that aren't the most important to them. Okay? All right. For example, if you wanted to implement persistence in a system, you can run it, shut it down, come back to it. The data is still there. You could spend a month learning NoSQL and have a beautiful storage engine, or with something like CSV files, comma separated value files on a disk, suffice. You have to decide where you're going to spend your time. Okay? Any questions about this? No? All right. And this last one of the 4 points talks about impact. And impact answers the question, once you're successful, what has changed? What is bigger, stronger, cheaper, better, more efficient, what have you? And you can't just say it, you have to measure it. It doesn't exist if it's not measurable. This is where you get into the definition of metrics for success. How do you measure the success of your proposed solution? It could be you design a survey. Maybe you instrument something in the hallway and try it out. You have to measure the success. Now, it doesn't mean your system has to work. It could be something that doesn't work. Your results could be confirmatory or non-confirmatory. But the question is, why was it successful? And you have to measure what success means. Why was it not successful? You have to measure what that non-success means. Okay? Are there any questions about this? No? Now, oh, I already said that. So the prototype's purpose is to test your scientific or engineering question. And it's really important to have metrics outline how you're going to enterprise to measure the success. Okay? All right, any questions? No? All right. And so essentially impact says, how does your prototype from point 3 address the gap from point 2 for the target audience you've described in point 1? And you put it all together in a presentation, that's your report. You put it all together in a long document, that's your engineering report written. Now, there are some undergrad examples. I won't show these. Please take a look at them. But when you take a look at them, keep in mind that they spent the whole semester, to my students, Jorge, George, and Kamlin. Jorge is at Bank of America now. Kamlin is a software engineer at Apple on the OS team, operating system team. And so with an eye towards these 4 points, you can actually pick out all of the things they've done in the 4 points. It's very, very prescriptive. And you'll get a chance in this class to practice it again and again and again. Okay? All right. Now, this is something that you learn in industry, right? I haven't seen it in any textbooks. And hopefully by the end of the semester, it'll be among the many tools in your toolbox, so to speak, to help give you some career type training before you graduate. Okay, oops, excuse me, sorry about that. Okay. Any questions? So please watch this. I apologize, I did a crude editing job. There's some music and all sorts of stuff. For us, Capstones was a 1 semester research project that started the semester before, but they both do a great job, and all the Capstone students go on to do fantastic things. And whether you keep things like a notebook in a blog, they just say, hey, take a look at my blog as part of their recruitment process, and they get to see all the wonderful things that students have done. All right, so we won't go over that. Let's take a look at the bounce chaser experiment. And so these are the parts list. You have the Arduino Wi-Fi 2. You have a breadboard, USB cable, jumper wires. There are 2 different types. These are the jumper wires that are in one of the plastic bins. These are, I think, in a box. You can use either one, right? These are used as conductors because there are copper wires inside of them, and you're going to use these to connect together the components on your breadboard. We have some resistors that you're going to use, 4 of them, 220 ohm, and some LEDs. Just pick a color, it doesn't matter which one it is. Oh, well, not white LED because it's a little harder to see. But that being the case, for the bounce chaser, you're going to start out with the LEDs arranged in a line, horizontal line, and you're going to start out with the left-handmost LED being lighted, and the lighted LED is going to change by going 1 LED to the right. So it's going to keep going 1 LED to the right. Once it reaches the right-hand extreme, it's going to reverse direction, and then this lighted LED is going to go to the left. So it's going to keep doing that left and to the right, and it's going to keep doing that again and again and again. Okay, any questions? And that's called the bounce chaser. I'm calling it bounce chaser. It's like a chaser circuit, but it's bouncing as it gets to the extreme. Okay, and so as part of your investigation, I want to put you in the posture of questioning things. And as you enterprise to answer these questions, write them down. And you're going to write them down in a lab notebook. Now, in research, a lab notebook is immensely important, and engineers live and die by their engineering notebook. It allows you to pick up where you left off precisely. And so if you're working on something, what happened? Why did it happen? Where did you find it? You should be able to consult it, aha, and then pick right back up from what you've logged down. It doesn't have to be fancy, but questions you answer, things like, for this example, some motivating questions. How do I log entries in a notebook? Okay, the research notebook, I'll show a slide for that. How does a breadboard work, right? That's partially in the book, partially in the video I've recorded. How do I build circuits using a breadboard, right? Push the pins in, answer that for yourself. Don't be satisfied leaving things unturned that you need in order to be successful, okay? How do I use the digital I/O pins on the Arduino IDE? You set the pin mode for the direction, inbound or outbound, and then you choose the pin, and then you do a digital write, right? How do I use the digital I/O to light an LED? You can't just do it directly. You need that resistor in series with the LED. How do I know if a resistor is 220 ohms? We have the color codes that talk about how to read the value. Yes, absolutely. In one of the component kits, it's written on a little piece of tape that tapes together the resistor, but you should be in the habit of reading that for yourself from the color bands. How do I write a finite state machine? We just went over that, okay? So don't be satisfied with having questions. Write that down, and I'm also more than happy to point you to useful resources, okay? All right, any questions? No? All right. And so don't just jump in and implement it. Plan it and design it, and your implementation will be much more smooth. Absolutely, there'll be weird glitches. With Arduino IDE, if you have it open for a while, sometimes weird things happen. Sometimes you'll have to exit it and restart it. Sometimes you'll have to reinstall something, right? It's a little bit wonky. That happens sometimes. And so this is the circuit that you'll be using. It'll be replicated 4 times. Your plus 5 volts will be provided by digital I/O. And when you send out a logic low, it'll be 0 volts. When you send out a logic high, it'll be plus 5 volts. So that's providing the electromotive force that we talked about. Then you'll have it going into a 22 ohm resistor. That 22 ohm resistor will then be connected through a conductor to a light emitting diode or LED. And you have to make sure it's connected to the anode, the positive side of the LED. The positive side or anode for the LED is the one with the longer leg, right? As we had discussed. And then you're going to connect it to ground. What ground are you going to connect it to? On the Arduino board, there's a connection marked ground. Okay. Now that resistor is there to protect the Arduino board and to protect the resistor, I mean, rather to protect the diode, the LED, because you're going to have too much current and you could burn things out. You don't want to burn out your board. Okay. Any questions about this? No? All right. So this is an example research notebook. It doesn't have to be paper. It can be digital. In fact, for research notebook, for robotic stuff, I like an actual paper notebook. But for other things, I just have a Microsoft Word file. Now, it's important to put a date on it so you know when you did it, right? If you're doing things multiple times a day, maybe you have the rough time when you did it. So you know what was the last thing you did, what happened before. Then I like to have sections and then who's present. It's important if you're working with others to know who is there, because maybe you have a to-do item at the end to email these people when you're done with your component. You're working on one part of the finite state machine, you're going to send it to one of your partners. Who are you working with at the time? Who did you talk to about it? Because maybe one person wasn't present and you're going to have to fill him or her in, right? Then what you did, bulleted list works well. You can add pictures, whether hand-drawn or digital pictures, useful sites where you found stuff. right? Because maybe you're not going to find it again. Say, oh gosh, what was that thing I saw? So you copy and paste a URL or link somewhere. It's really good sometimes to save a PDF in a Dropbox folder or a scan of a website, because sometimes useful things go away, right? And that's, I knew it was there. It's no longer there. What do I do now? All right. I personally use Slack for some things. You'll see some private Slack channels. That's where I accumulate documents and links to things that are important for this course before I curate it and put it on the Moodle site, right? And so whatever works for you, doesn't have to be paper. You could have a blog. You could have a GitHub site. Whatever works for you, whatever modality works for you is fine, but keep a notebook of what you've done. For example, how do I add a library to a sketch in the Arduino IDE? A little blurb, such as how you do it, through the menu choices you select, could save you a lot of time when you're trying to pick back up from where you left off. So reflections, you're gonna forget what you were thinking and why you did stuff at the time you did them. Write it down in your research notebook, okay? And that'll also make your reporting much easier, because it's just copy and paste if it's in electronic form. All right, any questions? No questions? All right, and in fact, in industry, on large scientific and engineering projects, your research notebooks, when the project is done, they get archived and they're part of the intellectual property of the company. And when they go for patents, those are part of the evidence for the lawyering that happens when you're applying for a patent. And so whether it's drug design, system design, mechanism design, these notebooks are very, very important. And its purpose with logging what happened, but also facilitating your ability to easily pick back up where you left off. Okay? All right, any questions about this? Does that make sense? All right, and so that is, well, second to last, APIs. This is a repeat of what I said earlier. You have two entry points on the Arduino. In any program, you have the setup, which is called one shot when you power it on or plug it in or reset, and then the loop, which is repeatedly called. You can have your includes here. That's to give you the definitions of libraries usually that you're going to use, and that should be accompanied with adding the library to your sketch. Then you have a section for preprocessor commands. This is just to make the programs look nice. A section for global variables, making sure to initialize them. It doesn't initialize it like the Java VM initializer. You have to do it yourself. Okay, any questions? Final questions about this? No? All right. So these are the APIs you'll be using. Pin mode, and when you use these APIs, it's C++. So every statement you call, you have to end it with a semicolon. It's a C++ requirement. Pin mode allows you to set the direction of a pin. So the digital I/O can be input or output. If you had, say, pin 13, you have to use pin mode in the setup in order to say, I want to send digital output or I want to read digital input, right? You have to control the pin as to which direction you're going to either send or receive data, okay? Is it inbound or outbound, your use of the pin? Then digital write is how you actually set the pin to be a logic 0 or a logic 1 or high or low, right? When you do a digital write for that pin to a high, it's going to set it to 5 volts. When you do a digital write for that pin to a low, it's going to set it to 0 volts. Okay. Any questions? No? Yes. Yeah, I'll leave it up after I'm done. And then I'll leave it up for the entire afternoon session. Okay. Any other questions? Now, again, thank you for the question. You shouldn't just be implementing finite state machine. You should be going through the process of designing your finite state machine. Okay. All right. So serial begin takes a parameter of the baud rate, and it's how you turn on the serial terminal so that all the print statements for your Arduino will make their way out. Now, serial print line is how you print something to the console, but it includes a new line. Serial print prints, but it does not include a new line. This block here, while not serial, with an empty statement, that's what just semicolon means with no function call. That's how in the setup, you wait for your serial port system for sending input and output text, rather sending output text. That's how you wait for it to wake up. Once you say serial begin, you need to say while not serial, empty statement, waiting for this serial port to open up, right? So you can send things back to the console from your Arduino out to the terminal in the IDE. And then of course, switch and case. All right, any questions about this? Make sense? Yeah, all right. And so that's all I had. I will leave up the finite state machine, but I wanna stress, it's not copy the finite state machine. Go through the exercises, enumerate your states, have your loop sandwich, have your cases, wire in the transitions, do it incrementally. It's a recipe for disaster to try to do it all at once. The process works, okay? All right, so let me stop the recording